are catching up on the stream with us, so I think it's time we begin. I'm Zlatko Minev from IBM Quantum Research, and I'm thrilled to roll out the latest episode today of the IBM Qiskit Live Quantum Seminar Series dedicated to you and to the research and academic quantum communities. Today I have the extreme pleasure and privilege of hosting Frank Wilhelm-Mauch from Saarland University and the Research Center Jülich. Hello, Frank. How are you today?
Hi, Zlatko. I'm great. Where I am, it's already Friday evening, so this is a great conclusion of the working week.
It's wonderful to hear, Frank. I guess you're ahead of us, not only in your knowledge in superconducting quantum circuits and control, but time. And I hope I can wish you an almost happy birthday.
This is definitely the last research seminar I'm giving in my 40s.
So I hope this is a good and special one. So happy birthday wishes from me and from everyone in the audience to you. Before we begin, I'll give a bit of background. If you allow me, Frank began his scientific career at the University of Karlsruhe in Germany, where he obtained his Vordiplom, or BS, in 1993 and doctorate in 1999. He started working on quantum computing very early on in 1999 when he joined the experimental group of Mui and at what is now known as the Kavli Institute of Nanoscience at the Delft University of Technology, Kavli Institute, in the Netherlands. Still being a theorist, Frank moved to the Ludwig Maximilian University of Munich in 2001, and then in 2006 he joined the University of Waterloo, Canada, as an associate professor of physics at the IQC, or Institute for Quantum Computing, and became a full professor in 2011. He has since become a full chair professor in Saarland University in Germany in 2011. I think I got that right. And Frank has since done many things, which I can only list a short number, including divisional associate editor at APL. And he's also currently the coordinator of the very large flagship Open SuperQ project, as well as he's currently heading the Institute for Quantum Computing Analytics as its director at Jülich. So Frank, we're very glad you could join us today. The stage is yours.
It's my great pleasure, and kudos for suffering through all of these long and hard to pronounce German names with funny sounds like the CH.
Danke, danke.
So this is, again, a talk about optimal quantum control for superconducting qubits, which we have done for quite a long time. So it's a work of, in fact, many generations of people. So you see parts of my group in Jülich here, but also Daniel Egger, with who we did this at IBM in Rüschlikon. But his contributions were also historic in the ramp up to the latest results when he was my PhD student. And unfortunately, with the setup and all the intricacies of multi-screens, I don't have a pointer, so I will play radio. I always will tell you, look at the left and at the right. So the latest of this work is actually coming from an initiative that you see in the sponsors gallery called Cusco, which is an activity that tries to give very specialized graduate education to PhD candidates in the field of quantum optimal control, where no place alone has a critical mass for dedicated programs. So this is a Europe-wide activity, and this is actually where I met Zlatko last time, back in the era when we were still traveling. So I assume that most people here have some knowledge and understanding of quantum computing, and maybe have heard about superconducting qubits, but probably not all of you have heard about quantum control. So I will explain a few nuts and bolts, and then explain why it's actually quite difficult to apply this to superconducting qubits in the right way. But I will show you then an evolution for how we use this to find a tool called drag, which I will explain. But how after discovering these pulses, we needed to find a method that actually closes the loop of optimal control between the controller and the system, and then also put system characterization into the mix. And then there will be an outlook in the end. You see quite a few bullet points, but actually one of these bullet points only contains one slide. But that also means that We do not have to go through all of this. If people have questions along the way, please ask them via Zlatko. I am way too old to watch a chat at the right time. And it's much better if we only cover half of it, but really get a common understanding of the topic. So motivation and nuts and bolts. I'm showing here spectacular great experiments, the famous quantum supremacy from Google, and well, IBM's recent best. IBM is, of course, always improving as a representative from this work from last year. Both of these are really big chips with 53 qubits, and the largest IBMs when I made this slide was 65, and they're ever growing. The precise size is not the point. The point is that the performance here is clearly limited not by the number of qubits, but by fidelity and by error. The cross-entropy benchmarking setup was designed cleverly so it could make a statement about the quantumness of the system, even though in the end it was overwhelmed by noise. And at IBM, the quantum volume measure, where you're running a square circuit with a 2/3 success probability, pointed that you could at max for this measure use 8 qubits, which is clearly much lower than the available qubits. So for progress in quantum computing, really dealing with noise and increasing fidelity is the order of the day. Now, generally, as a community, what can we do with this? We can, of course, remove sources of decoherence. We can make cleaner samples. And there is a lot of ways to do this. But of course, sometimes we are running in a situation where the cleaner sample is less flexible. You are removing some options you have when you're removing noise. And quantum control can, in principle, happen to identify what is the degree of flexibility that you still need to actually build a quantum computer. You can also decide to outrun decoherence. If decoherence sets you a certain time limit, T1 and T2, one way to make best use of it is just to operate as fast as possible. And if those coherence times remain fixed, if they don't increase by what you do to the sample, that gets you more fidelity. You can also use smart strategies, and I will outline one of them, which is kind of a historic milestone of superconducting qubits. And then use some additional optimization to essentially avoid the impact of decoherence without removing it, but with designing an experiment that avoids its impact. Also, not only decoherence is limiting performance, there are coherent errors. There can be slight misrotations. There can be degrees of freedom in your system that are themselves very coherent, but that perturb the system. There can also be some deformations, some lack of characterization that you would like to control. And again, this is shown in blue because optimal control can help with this. And of course, it's always important to, while you are making optimal use of your system, find any unknown unknowns. I'm quoting an ex-US defense secretary whose views I in general do not endorse. So characterizing your system better and better in order to find noise sources is also on the wish list. And all of these things pointed in blue are areas where optimal control can help. So what is it? Essentially, we take a piece of hardware. Sorry, Google makes slightly sexier pictures than IBM. This is also pre-Google. This is still UC Santa Barbara. Here is a chip with quantum hardware. You see the qubits as crosses, you see drive lines, you can see readout lines. And they will never be a perfect Hamiltonian, starting with the fact that there are no perfect two-level systems in the world. Even the famous spin 1/2 particle is not a perfect two-level system because the spin 1/2 is attached to a particle, the particle can move, and so it's never perfect. And we are also, now we want to use a control system. So we're using an electronics box that is connected to the sample at room temperatures in order to make, this is shown in the middle, In order to make the gates, I need to remember that I'm actually saying what I'm now looking at, in order to make the elements of the quantum algorithm to the right as good as we can. So we want to minimize the gate error, which is measured as 1 minus the fidelity. And if fidelity is high, then error is much easier to understand measure. We want to make this work under realistic conditions. So we want to make this work not for a oversimplified model of the chip on the left, but for the real system. And we want to do this using systematic methods because it's too hard of a problem to kind of just use workaround by hand. So what do we really want? For making a universal n-qubit quantum computer, we want to generate what is known as SU2 to the n. So what is in this expression? 2 to the n is the dimension of the vector space, the Hilbert space that contains the qubits. And we are basically saying we want to make all unitary operations, which we in the first step break up into single qubit rotations and a 2-qubit gate that creates entanglement, ideally that creates maximum entanglement. And we need to figure out how to way to make them. And if you look at a textbook, if you look at Nielsen and Schwang, or also newer textbooks, they typically have some recipes that people have figured out how to make them. But just figuring things out is not enough. We want to be a bit more systematic. So how are we more systematic? Well, suppose the system is described by a Hamiltonian. This is an operator that characterizes the energy of the system and that drives quantum evolution, which we can usually split up in the form shown in what I just zoomed in. It has a component H0, which is everything we cannot change while we operate the system. This is the basic chip layout. And it also has a bunch of control Hamiltonians, HI. This is everything that you can actually couple into. And then UI is what is coming out of the pulse generator and entering, landing at the chip. So these are the control fields. And there is a mathematical construction that shows you that if the H0 and the HI are general enough, if the so-called Lie closure, which is the set of all commutators, is large enough, then this allows you to build a universal quantum computer. And this is already a tool to tell you, oh, if I want to close my system more, if I want to take controls away, what is it that I need? But then you go for a second step. You're saying that my gate, now I'm looking at the equation on the lower left, that is should be the gate that I want to put into my algorithm, that I want to put into the Qiskit circuit, needs to be a solution of the time-dependent Schrödinger equation. So it needs to basically be this time-ordered exponential, which is basically saying we are solving the Schrödinger equation. But if you now look at go up to the presentation of the Hamiltonian further up in this column, we see that this is how the control enters. The UI of t enters the bracket on the left. So we can now engineer those functions, UI, what is coming out of the pulse generator, in order to reach our gate in the best possible way. And now if you look at the curve in the middle and on the bottom, you see kind of the basic way how you would do this. This is an initial guess for the pulse shape you're taking, something you've probably taken from a book for a slightly simplified model. And now you read this from the right to the left, because it turns out that you can compute, if I jiggle around with the last time slice with the capital N inside, I can pretty much see what it does to the gate and how it changes, gets us closer to the gate we want. I can compute a gradient and how the gate changes as a function of this amplitude, and I can use the gradient to improve that time slice. And then I'm going to an earlier time step, and I now know where do I have to be to land on the right gate. I can compute the gradient. So I can go from right to left, compute a gradient of my pulse shape, and by this improve it to a gradient search. So for example, the error is set to a minimum. This is textbook optimal control. On the bottom right, overlapping with my employer's logo, is a paper called Training Schrödinger's Cat, which is a great reference to this field in general. And here is a typical output. It actually has a sample number of experimental colleagues, what this looks like. You're getting a wild pulse shape that is not very intuitive, that somehow magically gets you the operation that you would like to do. So there is a question, how can we apply this wild pulse shape that we got from doing this gradient search? Well, here's another example of a wild pulse shape where we've basically taken a model, we went to the computer, we optimized this, and it shows that the beloved cross-resonance gate of IBM can be optimized to get to rather short times with some rather advanced pulse shapes. And at the time when we did this, it was beating all of IBM's records. I think now IBM is actually faster. But this is just, and this was from an honors thesis of an undergraduate student, also demonstrating to you that this is a fairly reliable technique that can be picked up quickly. So that, however, has a problem. And the problem I've already shown you, it is that the Hamiltonian of the system is the crucial ingredient to this work. And when we tried this in 2014, we saw that, well, if the model is slightly wrong, if the Hamiltonian is slightly wrong, we are going to an extremum. What you see on the lower left is the error landscape. What happens if the system is slightly mischaracterized, if we have the slightly wrong model? Then we see, well, the ideal point is where the lines cross, is a maximum. A maximum is a point where the landscape is flat. So small errors don't harm us, and that has been the gospel in optimal control for a long time. However, practically, this landscape is so steep that the first order flatness doesn't help you. You're always in high order. And it was, which means that we have to characterize your system with very high precision in order to apply this, in order to have a Hamiltonian that is good enough to enter the scheme from slide 7. Now, we got the academic honor that our error landscape was so beautiful that we made it to a title slide of a journal, but that does not solve the problem. So where is this coming from? Well, in reality, the model that I've put out is wrong, and specifically in human-made systems, in solid-state systems, it's typically wrong in the sense that there's junk in the system. And the junk can have two forms. It can be an unwanted degree of freedom, an unwanted resonance, an unwanted standing wave. Or it can be that the parameters that your system has are not what you think they are. They are slightly wrong, or they may even drift during your experiment, because keep in mind, quantum computing is precision science. And if we want to have a 10 to the minus 4 error, we'd better know our Hamiltonian with a compatible precision. In atomic physics, this is not the case, because in atomic physics, oftentimes, if your qubit is from the periodic table, chances are it has been characterized with extreme precision. Now, where does this come from in a practical example? Well, our beloved qubits, they have been fabricated, and we have characterized them well, but there will still be some errors. They drift during the day. But there is more. You are actually sending in your UI of t, your waveform, from room temperature. You run it through filters and through an antenna to get to your chip. That will distort the signal. So even that translation you do not know very precisely. And on the bottom, in panels B and C, you see another example for a very steep landscape. In B, you see that even the flat extremum at 0 is sometimes not visible. So these are the different things, and actually it's very hard to even predict the electronics chain, because when you swap out a test chip from a qubit chip, everything will change. Now, there have been good solutions for this, specifically from Yale, where people said, well, there are situations when we can characterize the system extremely well, specifically in the so-called 3D transmon. But when you put more qubits into your cavity, that also changes. And also, they have restricted themselves to a rather narrow bandwidth in which it is possible to get a very good model that just covers this narrow bandwidth, which you can see by the fact that the time axis in the left panel B is 500 nanoseconds, and the time axis that I've shown you 2 slides ago was an order of magnitude shorter. So in order to unlock the full potential of making really fast gates, having this model on the narrow bandwidth won't get us all the way. Here's a specific nasty example, also unfortunately with nasty resolution. Sorry, my art skills here are limited, of a defect which are two-level systems. This is all kinds of fabrication dirt that appears because the materials here are amorphous, and amorphous materials are known to have uncontrolled degrees of freedom. And when they are at the wrong point, they can actually perturb you quite a bit. And as you see on the right, these are avoided crossings. These are signals of a coherent two-level system coupling very well to your qubit. And they are inevitable. They appear sooner or later. If you have a good fabrication process, they appear later. This is an example of an extra degree of freedom that you better take into account when you want to make a high precision experiment, and that you also need to discover when you make your chip, when you characterize a chip. So this makes it very difficult, but historically, we have been able to do a shortcut, namely to use quantum optimal control to find a very simple strategy that works across the way. So the superconducting qubit aficionados will be bored the next couple of slides, but not everybody is that. So let's look at this. So first of all, we wrote a paper in 2018 summarizing everything on the next slide, which was celebrating 10 years of the so-called drag strategy, which I'll explain to you now. And we were slightly scared that it has already been 10 years. And this is based on a rather unusual observation, and I now need to play out my age of that I've been with superconducting qubits for a long time, is that the nonlinearities in superconducting qubits have been shrinking over time. On the left, you see a micrograph, an electron microscope picture of the Nakamura setup from 1999, which was the first successful experiment showing a single qubit gate on a superconducting system. And the one thing, just as a bit of history, what you see is amazing is the scale bar. It's 1 micrometer. The qubit is actually under a micrometer in size. There has been an evolution on the on the top, on the right column, you see quantronium, which is an evolution from this Cooper pair box, which is a fair bit larger already. And as the final step of this evolution, on the lower right, you see a transmon, and you see the big, well, it's probably hard to read if you have a small screen, but you see the scale bar on the bottom right is 290 nanometers. So this is a micrometer. So this is 300 times bigger than the first generation. So talk about anti-nanotechnology. Our qubits have become bigger. The active part, the Josephson junction, only became a little bigger. It's this big capacitor which makes this big. What makes this interesting for coming back to our story about optimal control is the evolution of nonlinearities, shown in the middle, going from panel A through D. You see the energy levels 0 and 1 shown in black and red.
I think so. I don't hear anything. I think we'll be coming back because I can see the slides changing. Hey, Frank, I don't know if you can hear us, but we're having a little... Oh, I think I can see your screen moving again, and I can see your image moving again.
So, but you do not hear my audio, is that correct? Do you hear my audio again?
You are back. I can hear you.
I am back. You can see and hear me, so I go back to projecting with the modern technology, and probably everybody around me is switching on YouTube right now, or Netflix. So if you hear me okay again,
I think
it's
we're
Friday
good.
night. So, okay, so you see that in the transmon, the splitting omega 1,0 and omega 2,1 are very similar. So qubits also have become more linear. And that's a problem because there's a theorem due to Husimi from the 1920s that if we are driving a harmonic oscillator, we will never be able to sharply get from 0 to 1. We need a bit of unharmonicity, a bit of difference in level splitting to do this. And there's a simple spectroscopic argument. If I want to resonantly go from 0 to 1, And if omega 2,1 equals omega 1,0, I am continuing resonantly to go to a level 2. So here is something to do, and this is the solution. This is the situation again, and the problem that we faced 10 years ago. So if you look at the middle panel, the left panel you have just seen, basically, if the transition frequency omega 0,1 and omega 1,2 are close to each other, and if you're driving a pulse that is very short, then the frequency width will be proportional to 1 over the gate time. That should be a 1 over in the middle panel, 1 over T gate. So if I drive my system too fast, if I want to really squeeze a lot of single qubit gates into my coherence time, I will start driving the other transition. And in fact, on the right, you have seen the Yale and the Santa Barbara group, which now have morphed into the IBM. Well, there's still a strong activity at Yale, but which has now spun off the IBM group, and which now has become the Google group. They have both seen the plot on the right, where they have shown single qubit gate error in slightly different metrics as a function of gate length. And you see that if they make a longer gate, the error increases because of decoherence, because they are limited by T2. But if they go very short, at some point the curve turns around and the error also grows at very short times. And this is precisely seeing spectral crosstalk between those two lines. Now, we actually turned to a lot of numerics. If you read the old drag paper from 2009, you may wonder, how did they come up with this strange analytical argument? We didn't. We did numerics-driven discovery, and we could show by essentially analyzing numerical results that if instead of only driving your carrier envelope with a cosine omega t with some envelope u1, you need to also drive the outer phase component sine omega t, and the prefactor, the envelope, has to be proportional to the time derivative of the first envelope. This is called drag, derivative removal by adiabatic gate, and it has worked like a charm. The same two groups published papers shown on the lower left that indicated a strong improvement. For example, on the very lower left panel, you see that the Yale group could make more than 90 gates before getting close to 1/2, whereas without drag, which is on the top, it went a lot worse. We were then able to improve it. We were also looking at what happens if I put another qubit next to it that is also very close in frequency. And we could come up with weak anharmonicity with average Hamiltonian, called WAWA. Reverse acronyms is very important in control theory. The NMR people are also doing that, which essentially has the same structure as drag. So you see in the equations in the middle of the screen that omega y is still proportional to omega x, and omega is our symbol for the envelope. But we also have to have a very specific form of omega x. And the group of Leo Di Carlo has shown on the right that the WAWA has a big improvement. Specifically, if you look at the right column, panel B, the upper panel, they went without WAWA with the red triangles all the way down to blue. And that was important because that meant actually with two qubits next to each other, they were as good as with one isolated qubit, which was the purple curve. So these strategies work, and the reason why they work are the equations that you're seeing here. These strategies are so simple that you can just feed them into the usual experimental modeling process and everything works. So we have this experimental task, remove leakage. We have done numerical optimization. So we ran our computer. We found a very simple shape, the equations from the last slide, and then experimentalists put it onto their toolkit and made it work. This is great, and the advanced version of this is this slide, which you have to take pictures of, which is to make this simple-minded theorist work flow into full experimental tune-up. And as the Google group likes to point out, 2 of these dots correspond to one PhD thesis. And now the goal of optimal control is to actually automate this, that it's not the creativity of PhD students, but the use of algorithms that can get us shortcuts and blocks into a graph like this. So we now need to essentially do optimal control, and make those complicated, non-intuitive pulse shapes work as well. And the idea of how to work this is shown here. What I've shown you on the last couple of slides is red, yellow, and green of the middle graph. We design a system, we characterize it, we do an open loop gradient search, so the gradient type of calculation, and we get something. And then, because the system is not well characterized, we want to still update the pulse. We want to adjust it to what's going on the experiment by measuring the fidelity and then updating the pulses in real time. And the analogy I like to use, you can then figure out transfer function errors, characterization errors. And the analogy I like to use is a person at a mixing desk at a rock concert who is actually also adjusting for the transfer function from the stage to the audience and the distortion of the signal by the presence of the audience and various miscalibrations, if the drum kit is funny and things like this. But that person is not doing this by a mathematical procedure which involves computing the transfer function. It basically involves that having two things. One is listening to what's going on and adjusting sliders. And the other one is to having experience with what happens. And I will now first show you how to adjust sliders, and then I will show you experience by using machine learning. Now, we need to do two things. We need to measure the fidelity well, and we need simple pulses. Now, for measuring the fidelity well, I'm sure many of you have heard about the wonderful method of randomized benchmarking, which runs a random gate sequence taken from the Clifford group that is easily invertible, and it gets us the error per gate. And it's not immune to the most main experimental restrictions. So if we essentially fit an exponential to the result of randomized benchmarking shown on the right, we can very reliably read out the error per gate. So that is easy, and I don't think I have to go into a lot of details. But the other thing is, if we do these closed loop pulse updates shown here, those are hard. They take a long time. Every update corresponds to running a bunch of experiments. So the other thing we need is actually simple pulses. I showed this to you in 2 slides. I just show for the randomized benchmarking aficionados one slide, which is extremely full and technical, which is that actually when you rerun randomized benchmarking, you don't have to reset because you're just looking for switches, for changes. If you start in the excited state, you just look for the survival probability of the excited state. And on the upper right, you see a typical simple optimization trajectory where you move along the gray points to land on the white point, to land on the optimum on your landscape, on the upper right. But you have to keep in mind that you have to take a lot of points, a lot of data per point, and you want to do this efficiently, and you want to have simple sequences so you don't have to adjust a lot. So for this, you need simple pulses, for which we have developed GOAT, which is a technique that essentially allows you to avoid, well, I show you what you want to avoid. You want to avoid something I've shown you very early. You want to avoid the plot that you see here, because that means that essentially you need to adjust every time slice of your arbitrary waveform generator, and only this way you compute a gradient. And we like gradients because they make us converge quickly. Because the trick how you derive the gradient crucially depends on stepping back in time. Now, we have found a method where instead of a parametrization by time slices, you can take a more convenient parametrization and still compute the gradient. And this is how it looks like. It's called GOAT. And this is what I actually used to find this. So here we have represented the pulse by a couple of Fourier components. If you want to go really fast, there is no free lunch. We still have to take a lot of Fourier components, but that has to do also with the information that goes into the pulse. But in essence, that allows us to use convenient parametrizations. And now experimentalists among you may say, but we have an arbitrary waveform generator. Yes, but Fourier representation is an information-efficient representation of your pulse. So that's what you want to use. It's really about making the tune-up quick. And we have also looked at a problem where you essentially have 2 frequency collisions, which I know are a challenge for IBM. And we could show that with rather complex pulse shapes, we were able to address frequency collisions. And of course, you're not drawing this pulse. You take this very high red and blue fast carrier frequency, and then you shape the envelope. So this is indeed quite powerful, and we can find simple pulse shapes. And now this allows us to essentially close this loop. We can do some pulse design, and then we have a simple pulse, and then we can do a real-time pulse update to make it even better. This is still great, but it has one problem, namely that if you have some uncharacterized aspects of your experiment that you don't quite understand, you have to calibrate them away again and again. And now, of course, you have intelligent people in the lab who see what's going on, but if complexity increases, we would like to replace intelligent people by pseudo-intelligent machines, and this has led us to a framework called combined characterization and control.
And Frank, maybe
because basically
into that,
yep.
Could you expand a bit on GOAT and more about how you pick the control Hamiltonians HK in the set of control Hamiltonians you want to go?
No, the set of control Hamiltonians is typically given to us by the experiment. If I am driving a qubit with an electric field, I have a reasonable model on what the control Hamiltonian is. The difference to previously was the ck of alpha and t. So this is a time-dependent function that is characterized by a set of parameters alpha that is not necessarily time-sliced representation. And the difficulty you indeed have is that now we want to compute what is the sensitivity of my unitary gate at the end of the pulse. So I want to compute this last line. I want to compute the gradient of u with respect to all of my parameters alpha. And the fundamental trick of optimal control is this back propagation. I know how it depends at the last step, and then I propagate my gate backwards, and I can get all the gradients. The way how we compute the gradient is slightly different. Namely, we realize by simple exchange of the order of differentiations that the d alpha of u at any given time satisfies a pseudo-Schrödinger equation. For the initial guess, we can just compute this. And for the rest, by simple chain rule and by knowing how the total Hamiltonian depends on alpha, so what we do to compute d alpha h is h is the complete Hamiltonian shown on the left. So we just need to differentiate ck with respect to its parameters. So if ck, for example, is a Gaussian, which has an amplitude, a time center, and a width, we know how to then alpha is a vector of 3 numbers, and we know how to calculate its derivatives. And so we actually never compute a gradient. We only pre-compute a gradient and then propagate it. And this way we completely avoid having to calculate gradients on a computer. And if we have the gradient of u with respect to alpha, we can get the gradient of the fidelity with respect to alpha and then do a gradient search. And gradient searches are important because this is going into the first phase of this design. This is done on a computer to get a very simple pulse. And there we want to reach high precision, and for this, gradients are the fastest way to do it. And another exercise is to get the representation sparse. And the way how we do that is we try a carrier envelope with a Fourier or a spline representation of the envelope. I think this was done with a spline for the envelope. And sometimes if that doesn't work, we just do a complete overkill optimization. We go with very fine time slice. We see what we get, and then we see what kind of functions probably fits this quickly, and then we simplify. Did this address your question?
Yes, I think that helps. Thanks, Frank.
Yeah. I don't see anybody given my setup, so. Because now we're coming back to how would you actually really choose HK? Because so far I told you this comes from the model that has been done. And I already told you that models are typically not as precise as we would like them to be. Now, Yeah.
I think maybe I missed one more question here from the audience, or two. I think one was about the physical meaning of alpha, but I think you explained that's if you have a Gaussian, that would be a vector of its three parameters, like the mean, width, etc. And another question was if you would mention if we need to consider the constraints of the arbitrary waveform generator relative to the waveform uploading for optimal control. I guess whether you, in this step, you worry about something like the bandwidth of the AWG and what it can do and so on.
We do worry about the bandwidth of the AWG. We typically, in the end, have to slightly fine-tune because we're discretizing the cosine again. And we sometimes have to put in, for example, also just power penalties. So, if the fastest way to make a single qubit X gate on a strict qubit is to just send a Dirac delta down, but you never have this resolution. And we typically don't implement this by constraints, but by penalties, because they tend to converge a lot quicker.
Great.
Does this answer the question?
Right.
Okay. So the fine calibration loop is something we can do, and in the end, we always have to do, but we want to do it as little as possible because it's quite costly. So ideally, pulse calibration, the fine-tuning, the mixing desk situation means our model is slightly wrong. And if we just calibrate it away, we don't learn anything. So now we want to have our person at the mixing desk. I actually need to show mixing desks in the next version of this talk. Is to gain experience and learn something about the model and getting a good model. And you see in the bottom half of the left column, we actually capitalize this because in the paper we have on this, we have a formal definition of a good model, which is it predicts the behavior to the accuracy we care about, which is 1 minus 10 to the minus 4. So we are really way above an error correction threshold. And if we have a model that has this predictive power, that is our goal now, we can find very good gates without a whole lot of calibration. And we can also understand the error budget. And I think my impression is, I certainly don't have a complete survey of literature, and probably this is something also people keep internal, that a complete error budget of a very mature quantum processor is very hard to come by. So can we do something here? Well, here is the workflow that we have implemented, shown on the right and described on the left. So the optimal control from the very beginning of the talk, we can now call C1. This is open loop optimal control. We're getting some model shown in purple from an experimentalist, and we optimize pulse. And we get some fidelity out of it, and we get a gate set that then we calibrate. This was the chapter of the talk right before this. So we fine-tune. We store this in a data set on experiments and results. And then if we have a data set, we do another gradient search, or better, a search by automatic differentiation to improve our model, to learn what it was that we have to change in the model. Do we have to tweak parameters? Do we have to add or subtract anything? Given the trajectory of calibration we just had. And this will hopefully improve our model in the next run. So the idea is that you start from reasonable gates, about 80% fidelity. You do this optimal control. You do model-free calibration. This is the C2 step. And then you improve the model with C3. And then it hopefully converges. And the long-term goal of this is that you can essentially automate a 100-qubit chip with one click over the weekend. Over the weekend is important here because the idea is that it has very little human intervention. So again, these are the 3 steps, and I've already shown you GOAT and regular optimal control for first step. I've shown you ad hoc, this other looped diagram for C2, and now for C3, what comes out of machine learning, I want to illustrate to you in 2 examples. So here we have taken a single qubit that also has one of these nasty 2-level systems sitting close to it. So it has an unharmonicity parameter, delta omega. It has, delta omega is a line response. So let's go on the right column first. We assume that what arrives at the sample, capital omega, as a control is slightly distorted from the voltage V that is coming out of the pulse generator. We assume that we have a certain pulse generator. We do randomized benchmarking with a technique called orbit. And we have some fidelity, and we have model parameters. For example, GTLS, which is the coupling strength of the two-level system to the qubit. It is detuning little delta, the anharmonicity little delta. It's the resonance frequency of the qubit. And here we have used the C3 machinery to, in a couple of iterations of the algorithm, improve the fidelity. And you see that around step 6, where the fidelity starts to saturate, we also get the parameters for characterizing the system out really well. So this is not really model learning yet. This is essentially doing pulse optimization and spectroscopy, and finding the parameters of the model at the same time, which is not yet a tool for discovery, but it's certainly improving. We're doing two things at the same time. You also see that even while the fidelity is stagnating around iteration 20, some of the parameters like GTLS or delta Q in the plots are still improving, telling you that we have reached a strategy where they are not that important. The bad thing about this plot you see is the left axis. It saturates at a fairly high error. This is F. It should be 1 minus F. Sorry about that. It saturates about an error of, 60-something%. And this is because we have not put in any decoherence for the qubit itself. If we put in T1 and T2, so what we have done here is, if we put in T1 and T2, we discover that now it converges really well. It converges to a much better value, and it gets us the value of T1 for free. So in real AI, you would do model learning that allows you the option to have a T1, that allows you the option to have a couple of two-level systems, and for example, use a step like this to also count the two-level systems. I've shown in red here, that is the line that you would have without T1 and T2, without Lindblad type decoherence. So this is a basic example showing you that in principle, for a single qubit, closing the whole loop really works. And now I show you slightly what we have achieved with this tool. And unfortunately, for the main thing, I don't have a real plot. So we're now closing the loop of the talk also. We are going back to our friend Drag.
Before we go there, we have a minute for a question.
Sure.
So F of beta is a fidelity of some kind between the experiment and the simulation based on this orbit protocol. But how do we interpret what 0.7 means? Or maybe I'm not so clear what this capital...
So this orbit is a variation of randomized benchmarking. So here we have reached a fidelity of 93%.
Okay, and
this was not IBM Zurich's best qubit. This was the one we had. They had in the fridge when we had the example ready and really needed this plot.
Gotcha. And so, can you also clarify for us at each iteration what is the data that actually needs to be taken?
So we are taking. We have essentially. Found before the iteration, we've had a guess of a set of single qubit Clifford gates. We have run them, and we have, on the one hand, slightly improved the pulse shape in the blue step, in the C2 step, and basically without any extra data, just from how we have seen how we need to change our pulse in order to get higher fidelity, we have improved the model.
Right, and maybe I get a little lost, but is this for a single qubit in this particular example, or two qubit gate?
This is a single qubit that has an unfortunately closed two-level system.
Gotcha. Okay, great.
And yeah,
and then what you would actually have to execute on a quantum machine here is kind of what type of sequence, or how long would that take, or how many shots? Maybe you can give us some perspective on that.
I do not have the numbers, but it is regular randomized benchmarking for a single qubit.
Okay.
And you're running a couple of generations. So basically, you realize your pulses were slightly off, but your calibration algorithm tells you how to change them. So how to slightly change your carrier frequency, how to slightly change your drag parameter, and how to slightly deform the envelope in order to deal with the two-level system. So the new thing was that we also essentially, by data that we have anyway, we recycled those data to say that, by the way, this little dent in the envelope means the two-level system is here or there.
And is each iteration a series of randomized benchmarking protocols, you said?
Yes.
Or it is a series. Okay.
It's a series of so we have one set of Cliffords, and we need to assemble them into a couple of sequences.
Gotcha.
The team is currently working on making this as data efficient as possible, because one thing is that when you're on a bad spot, you stop early. The other thing that is on our development pipeline, I've taken this out in order to keep time, is that once we do model learning, what we can do is use AI-based experiment design. We can say, we don't want to make a good gate now. We want to send a sequence to which our model is most sensitive, so we can tickle out this one hidden parameter. And this is a kind of a well-known technique. This is known in image recognition from AI, but we haven't fully implemented that yet. This is basically just taking data you have anyway, and that have some signatures of problems of your experiment, and letting the machine find these signatures.
Okay. So basically, at each iteration, you choose some gate set, you run a randomized benchmarking sequence, then you tweak based on that in terms of the way you run the pulses, then you run another gate set, and you do this, I guess, until some condition is met, and then you proceed to the next iteration.
Yes. And here we needed, for good fidelity, we needed about 12 iterations. Then we got a bit more from...
Is it important that it's orbit, or...?
No. We have chosen orbit historically. That worked very well, but we have tried other... we have tried fixed length, variable length, and things like that.
Okay, great.
This is... Orbit in this plot is a bit of a historic example. Great. Now, we try to see how far this technique gets. In this paper, which just came out. Namely, if you're an academic of my age, you're following the principle, if I have a hammer, everything looks like a nail, and we went back to drag. Because the simple drag recipe with the derivative is actually the lowest order of a perturbation expansion, and there are orders beyond that which deform the pulse even more, but they also get very sensitive to details of your experiment. And what you see on the left is the evolution of an experiment. You see an error measure, population of leakage states. There's a number of the sequence length. And first of all, the sequence length is quite long. That's good. But you see that the blue curves in panels C and D on the left, they decay at about 150 to 200. And we wanted to get this faster, so we essentially digitized drag. PwC is not the name of a consulting firm, it's piecewise constant. So we digitized it, gave it the staircase shape that you see in panels A and B on the left. And we did the C3 loop run across it. And we saw that it got deformed quite a bit. A and B are the in-phase and quadrature amplitude. With the eyes of love, the quadrature is still very close to the time derivative of the in-phase. And in high order, it shouldn't actually be too close. And we got a very good improvement of using this sequence in the sense that we got a lot less error, even in long sequences. You've shown it a bit more on the right, where essentially see that drag has its limits at short gates. It only gets you to the very shortest gate, to the quantum speed limit, if you apply a lot of corrections. And with the strategy that was calibrated with this method, we have actually found those corrections. because you see on the upper right, the red curve is actually flat until the very shortest time. Basically, and this is a very well-known phenomenon in optimal control, is if you want to hit the quantum speed limit where all the curves end, you need more and more parameters. The pulse becomes more complicated. But you see here that with this method that we have just shown, we were able to tune up this very, very complicated pulse and still get it working, and got a significant improvement of fidelity, basically hitting the quantum speed limit. The fitted curve is very flat and it only breaks at the end. And I'll come to the reason why it breaks in a minute. And once again, before this, let me go to the lower right panel. This essentially shows how this was done. We have made, here would be Clifford gradient, which is a quarter turn. And this allows us to adjust the pulse shapes.
And
now,
Frank,
what you, yeah?
We have a question from the audience. For the cost function here, we use especially in the previous slide, we use the randomized benchmarking fidelity, which in itself takes a lot of experiments. So would it improve in sense, would the results benefit from, in some sense, complete tomography as a cost function instead of the fidelity, at least for a single qubit?
For single qubit, maybe. Of course, for multiple qubits is prohibitive. In our thinking, the role of other methods of characterizing the process is that if you use randomized benchmarking for calibration, you should use something else for the ultimate control of success. Because randomized benchmarking has loopholes. A lot of them can, in principle, be fixed. Here, you would indeed get more information from tomography. You just have more parameters to play with. However, we haven't fully characterized that, but the feeling that we have is that the sensitivity of fidelity to changes of the pulse is actually very instructive. When we go through a couple of generations, like on this plot, we really see how does the fidelity change when we change something, and that at least allows the machine to infer what's going on even without tomography. Now, one interesting thing we had, which our experimental colleagues did not want to make a real plot of, is if you look at the upper right, the curves end. And we were hoping that we would actually get an extreme hockey stick in the right curve, that at some time we are exhausting the physical limit and the fidelity drops, because drag does not replace nonlinearity. It just allows you to get the most out of your nonlinearity, to exhaust it to its full limit. So what happened is that we actually discovered a limitation of making faster single qubit gates that we did not expect, but apparently other people had it. Namely, when you make a very fast single qubit gate, and you actually recognize that in the panels that show pulses, we have dimensionless units on the y-axis. You still need to transfer enough energy to your sample, so the amplitudes get higher and higher. And at the level, at the shortest pulses, the input line couldn't handle the input amplitude anymore and started strongly distorting the signal. It's essentially clipped. So we basically, did the heavy metal guitar of quantum control here. And what this teaches us, well, this is easy to fix, but what this teaches us is that if the need for optimizing pulses is taken out of the experiment, if you know this has always been optimized, you can focus on other topics. And I think this is something very encouraging. We didn't hope that we discover an accidental contribution to the error budget in the first full experimental application. If we still have a few minutes, we don't really have. So let me just give one thought.
We have a soft stop, so you can take.
Okay, let me go through this slide and then very fast to the other ones. Is that let's look at a bigger picture. Namely, the modern NISQ algorithms we know are essentially variational. So they are feeding back some result of a final run of the algorithm into the composition of the algorithm. Our gate design process, specifically the C2 part, is variational. We are measuring fidelity, and we are tweaking the pulse so it gives us higher fidelity. So this encourages us to think a lot more about analog programming. If we have the guarantee that our system gets us to the state preparation it needs to take us, it's not clear whether the best way to break up the variational parameters is the parameterization of a quantum circuit. It could also be the parameterization of a waveform. And we are very much encouraged to try this out a lot more, to essentially use optimal control to program a variational circuit, and to use simply the structure of the underlying algebra to make sure it reaches the right manifold of states. Here is a few examples from the Maryland group on the upper right for QAOA, from the Sherbrooke group related mostly to chemistry on the bottom, and from a group in Trieste related to finding linear schedules on the lower left. And we have done something similar as well. That would take a little bit too long. I've shown you a bit about quantum optimal control and what are the challenges of applying it to superconducting qubits. But we could meet them by really also changing optimal control. It took me a couple of years from becoming a consumer of optimal control theory in general, who happens to apply this stuff to superconducting qubits, to somebody who pioneers methods. But we have this method development. I also believe that superconducting qubits, which we have taken as the prime example of something that is difficult to characterize because it's human-made, I believe that this will come to other platforms as well. Certainly also to semiconductors, which are also human-made. But even in ion traps, where the qubits themselves, each calcium-20 ion is exactly identical to each other calcium-20 ion. But for gates, we use the trap degrees of freedom. So a challenge about characterization and drift occurs there as well. It's not as pronounced yet, but it will come there as we scale up. And if you want to look at the library that we have used in the last few slides, please look at q-optimize.org. And now I think we still have time for more questions.
Thank you, Frank. That's really good to see. I'm actually on the website as we speak to check it out. It looks very nice. And we do have a couple of questions. And folks, please feel free to post your final questions in the comment chat box located on the right-hand side or below on YouTube. And we'll get those up to Frank now. The first question here from the audience was, the C3 method appears to this person a bit like machine learning with added physics know-how. Would a brute force ML approach, where one just tries to optimize some large set of parameters, be at all feasible?
I've taken out that slide. There's a slide I have that is called "Where is the Physics?" Brute force ML approaches would typically converge a lot slower and to a lot worse fidelities, because it would take them very long to learn physics. So in our case, the physics goes into, for example, finding the right class of models that we would like to put into to start relatively quickly. So for example, a class of models is the general output of black box quantization. And the fact that these two-level systems play a role is something that it's much better to invest into the class of models you want to learn from to get faster convergence into higher fidelities. To kind of learn all of this background of 20 years of research on superconducting qubits, we would probably not have enough training data to do so. However, one thing, the problem with clipping the input line, this is something we didn't have in the model. This is something we just realized by hand. So to me, the role of the physicist, like in all tasks of automation, probably since the invention, I don't know, of the mechanical weaving machine in the 19th century is that human labor becomes more technical and more interesting. So physicists should now be more worried about, do I really have the right class of model? Are there things in my setup that my models do not yet contain because the testing of those models is done by the machine? But brute force ML, we would probably not have enough training data. And long before there was ML, it is well known in quantum optimal control. So when was this? In the early 90s, people tried to do completely model-free optimal control with genetic algorithms. And this, I think, is proto-machine learning. This was pioneered by Herschel Rabitz from Princeton. It works very well if you want to control complex chemical reactions where you do not know the reaction pathways. However, it is also known to typically saturate at fidelities of 90 to, if you're lucky, 95%. So you're never getting to very high precisions. Now, for chemistry, that's okay, but it's not okay for us.
Thank you, Frank. That's a good answer. So one other question from the audience here was, could you speak to how long these experiments took, I guess on human timescale?
So this experiment here took, I think this experiment took about a month because we needed to fix a lot of things while it was developed. Otherwise, where you're running, and also in this experiment, the machine learning optimizer was not very well coded. I do not have a very good answer to how long a streamlined version of this would take. I don't think it currently beats human beings, but the trajectory and speed that it takes is strongly improving.
Excellent. How would the variational idea scale to larger circuits? Just from 2-3 slides ago, the variational idea of running QAOA or algorithms like that. Yes, this one.
My expectation would be that it basically scales the same way as regular QAOA. The important identification that needs to be done to make the representation very efficient comes from here. So the Lie closure. So you, in order to be able to, for example, reach all possible final states, you need to make sure that the set of commutators. So this Lie closure works as follows. You take all the HI, including H0, you compute commutators, and then you have more operators, then you compute commutators again until you are saturated, until there are no commutators anymore. And then you're checking, is this a basis of the set of all, of SU2n, of the set of all unitary matrices of the dimension 2 to the n. And by this, you can also count which operation, how many generations of commutators you need. And that should give you a hint on how many analog parameters you need on the different terms in this variational algorithms. But this has not been fully analyzed yet. We are at the very beginning. Yeah.
So you wouldn't need to instantiate these matrices numerically for large circuits. Like you wouldn't have to have 100.
No. I mean, the idea here is that once you have typically these commutator constructions are very systematic. So once you see the scheme, you know how it goes. But you would run this then on an experiment. You just need, I mean, in QAOA, in a way, there is a very similar question. There people ask, what depth of the algorithm do I need to get a good result? And what I've told you, that we need to see how many generations of commutators we need, would already include the answer what the necessary depth is, because these gives you the number of parameters that you have to have free in front of a certain part of your Hamiltonian. But there is no complete theory of this. So the technical term is we want to translate the theory of reachability to this problem of general state preparation.
Thank you. And two more quick questions. There was a few questions about the cost function and randomized benchmarking. Well, these days, of course, is a suite of different techniques. And as you mentioned, randomized benchmarking, the standard version itself can be misleading sometimes, potentially. So have you thought about, or do you have a favorite protocol or a protocol that you're optimistic about that could give a more robust characterization?
So I would typically our approach is to combine different randomized benchmarking sequences. So if you're specifically concerned about leakage, you can combine leakage benchmarking, but also try to make sure that you're keeping the average fidelity under control. So randomized benchmarking is very efficient. If you're using this restless method that you don't wait for reset, it can be done very fast. Yeah.
Okay, so no one technique to rule them all.
I'm afraid not. No.
Yes. All right, and maybe perhaps final question here. Do you could you comment on the perspective, I guess, of applying optimal control algorithms on multi-qubit systems, not one or two, but order of even 10?
So I think so there is no limit in principle, and in fact, if it's a good way to address the spectator qubit problem. However, the one thing you have to pay attention to is modularity. The closed loop part becomes expensive because it's working in simulation. It has to work on a classical computer. And if you hit to the 10s and the 20s, you will not be able to do this part with very high precision. So then the calibration part becomes more important. I think ultimately what we have to do is to explore the limit at which we can treat a quantum processor as a set of tiles that do not perturb each other. So the goal for us in going to larger systems is to apply optimal control to a couple of qubits where we want to optimize gates and their horizon, at which we assume that there's a strong spectator qubit effect. I have not seen any method of calibrating a quantum computer that would work if the assumption that at some point you have non-overlapping tiles breaks down. If there is one of them, I would stand corrected. But this event horizon and the event horizon should be part of the tile. And then, well, one thing I should say, there is a technique called robust control, which assumes that your model parameters are fuzzy and unidentifiable. And that can potentially help you to deal with some influence outside the event horizon. However, it generally makes the gate slower.
Thank you, Frank. I think with that, we're really coming up to the end of the seminar here. So I'll let you say any final words or closing remarks that you'd like to share with us.
Well, thanks for having me. I think this is a great opportunity, and it's also a great way to give a talk in the context of IBM, meant to be a global talk and not having to travel.
Apologies aren't quite as sexy as the other ones you showed.
No worries. Also, I think really thanks for asking great and engaged questions, which is sometimes difficult in this remote format, but some of these questions will make us really think. And yeah, thanks for having me. And depending on where you are, your weekend may be medium close or really close. So enjoy the rest of your day and have a nice weekend.
Likewise. Well, thank you, Frank, for accepting our invitation. It was a real pleasure, treat, and privilege to have you here. Also, thank you to everyone who tuned in today for all the great questions. And as Frank said, making this engaging even through a virtual environment. This video will stay recorded and posted, so you can go back and rewatch anything that you might have missed. And otherwise, we will see you next Friday at noon Eastern Time on the Qiskit Live seminar series. Enjoy your rest of the day or night.